Assalamu alaikum students. The topic of today's video is reversible adiabatic expansion of an ideal gas. So first of all, you know that an adiabatic process is that process in which no heat enters or leaves the system. So I can say that there is no heat transfer in an adiabatic process. So in adiabatic expansion, Q will be equal to 0. So moving on towards the first law of thermodynamics, the first law of thermodynamics, it states that Q is equal to delta E minus W, and I have taken minus W because work is done by the system. And again, as you know that Q will be equal to 0, this W will go here and I can write it as W is equal to delta E. Again, I'm saying that Q is equal to 0 and this minus W when go here will become plus W, and work done will be equal to change in the energy. And secondly, as you know that in case of the work done by the gas, we take P dV. Okay, the work done by the gas we take equal to P dV, and this delta E, because as you know that work is done by the system, so in that case the energy of the system will decrease. Why the energy of the system will decrease? I can write this del E as dE. Okay, so why this energy will decrease? Because there is no heat provided to the system. Okay, when there is no heat provided to the system, then all of the work would be done at the expense of the internal energy. So when the work will be done at the expense of the internal energy, what will happen? The internal energy will decrease. Okay, so that will give me PdV is equal to minus dE. So moving on, as you know that the formula for specific heat at constant volume is CV is equal to change in energy divided by delta T. Okay, so change in energy divided by delta T is the formula for the heat at constant volume, is the formula for specific heat at constant volume. This dt will go here and I will get a value of dE as CV dt. Okay, so now what I have to do, I just have to plug in this value in place of dt. Okay, so now plugging in this value, I get P dV is equal to, in place of minus dE, I just have to write minus CV delta T. Okay, so let's just consider the 1 mole of a gas in case of an ideal gas, because again we are performing the calculation for an ideal gas. You just have to consider 1 mole of an ideal gas, and again you know that for the general gas equation is given by PV is equal to nRT. The general gas equation is given by PV is equal to nRT, and again we are taking 1 mole of the gas, so that will give me PV is equal to RT. Okay, and here I just have to plug in the value for pressure, so I'm going to find the value for pressure, and that is P is equal to RT divided by V. Okay, so I just have got the value for pressure, and which I'm going to plug in here. Okay, so first of all what I'm going to do is just to write this as CV delta T. CV delta T is equal to, and this minus will go here. I just have rearranged it, and in the place of this pressure I'm going to plug in this value, and this value is RT over V, and again the next thing is we have is dV. Okay, so now this T will go in the denominator here, and I will be left with dt by T, and again in this place I have minus R, and this V will go below it, and I'll get this. Okay, so now what I have to do, I just have to integrate both sides of the equation. Okay, so we say that this CV is independent of the temperature. We assume that the heat capacity at constant volume is independent of temperature, and we take integration just like this, dt divided by T from T1 to T2. Again here R is a general gas constant, it will have no integration, and then again this will give me V1 V2 dV divided by V. Okay, so now integrating this part of the equation will give me natural log T2 over T1. So plugging it in the equation, I get CV natural log T2 over T1. Again, this here will give me a natural log V2 over V1. To consume this minus, I just have to take this denominator up and this numerator down. Because while taking the denominator up and numerator down, this natural log will change into minus natural log. Okay? And again, when r multiplied by this, minus minus becomes plus, and I will be r ln v1 over v2. So on changing the numerator by denominator, this minus will consume with this. So I will be left with cl and t2 over t1. Okay, so now what I have to do is that I just have to plug in the value for r. Okay, so now plugging in the value of r, first of all, I'm going to write the equation again. That is CV ln t2 over t1 is equal to r ln v1 over v2. And again, the value for r is Cp minus Cv that we have just calculated in our previous video. Okay, and that is ln v1 over v2, and again we have Cv ln t2 over t1. Okay, this Cv will go towards the right hand side, and I'll be left with ln t2 over t1 is equal to Cp minus Cv divided by Cv ln v1 over v2. And again, this Cv we go here and here, so on dividing the denominator, I'm getting minus Cv by Cv ln v1 over v2, and again I'll have t2 over t1. So now this Cv will cancel out with this Cv, and there will be I'll be left with Cp over Cv minus 1 ln v1 over v2, and Cp minus Cv is equal to gamma, so I can write it as gamma minus 1 ln v1 over v2. And again, this is the rule of the log, that the power is present behind the log. So when I have to solve it further, I can take this part in the power. So that will give me ln v1 over v2 raised to power gamma minus 1. Okay, and on the left side I have is ln t2 over t1, and this natural log will cut down with this natural log. Okay, and I'll be left with t2 over t1 is equal to v1 gamma minus 1 divided by v2 gamma minus 1. Okay, so this v2 will go here, this t1 will go here, and then the equation will become t2 v2 gamma minus 1 t1 v1 gamma minus 1. And again, since as you know that t2 v2 gamma minus 1 is equal to t1 v1 gamma minus 1, I can write it as tv gamma minus 1 is equal to constant. So that is one of our relation between temperature and volume. Similarly, we can also calculate the relation between pressure and volume. For that, you again have to consider the general gas equation. The general gas equation says PV is equal to nRT. So if I want to find the value for 1 mole of gas, then that will give me PV is equal to RT. Again, I have to find the value of R, then R will be equal to PV divided by T. So when I'm taking P1 V1 over T1, then that will be equal to P2 V2 over T2. So I'm just going to write this here. P1 V1 over T1 is equal to P2 V2 over T2, and now I just have to rearrange this equation. This T2 will go here, this P1 V1 will go here, and then I'll be left with T2 over T1 is equal to P2 V2 divided by P1 V1. Okay, so now what I have just done is rearrange this equation, and now as you know that T2 over T1 here, from this you can calculate that T2 over T1 is equal to V1 over V2 gamma minus 1 and gamma minus 1. You already know this part here, so I just have to plug in the value for T2 over T1 from here. Okay, so now plugging in the value, that will give me P2 V2 over P1 V1 is equal to V1 by V2 gamma minus 1. Okay, I just have plugged in the value here. Okay, so now after plugging in the value, what I have to do is I just have to break this into two parts. So how can I do that? V2 over P1 V1 is equal to, I can write it as V1 over V2 gamma, and again this minus 1, I can write this minus 1 separately. Okay, I just have divided the power into two parts. Okay, again, as you know that if I want to convert this minus 1 into a into a positive quantity, then I can write it as V1 over V2 gamma, and in this to convert this minus 1, I just have to take the denominator up and numerator down. Okay, I've just taken the denominator up and numerator down. This minus 1 has consumed. Okay, so now I'm just going to perform the final calculations here. So I am left with P2 V2 over P1 V1 is equal to V1 over V2 V1 over V2 gamma and V2 over V1 V2 over V1. Okay, again, when this V1 will go here and this V2 will go here, they will cancel out with this. Okay, let me just explain it. Let me just take this V1 here and this V2 here, then it will be like P2 over P1 is equal to V1 over V2 gamma, and this is the V2 over V1. Again, this V1 has gone here and this V2 has gone here, and this V2 has cancelled out with this V1 has cancelled out with this one, so I'm left with P2 over P1 is equal to V1 over V2 gamma. Again, this V2 gamma will go here and that will give me this, and this P1 will go here and that will give me this. So I can write PV gamma is equal to constant. So that is my second relation.